Sir, we will wait a few more minutes. A few more students needs to enter. That's okay. Am I audible?
Yeah, you're audible. Am I audible?
Yeah, yeah.
Okay. Yeah, sure.
Tech Heart Homes. We fabricate your dreams as real. Fabricated villas, resorts, residential homes, hotels, QSR outlets, commercial places. We blend most sophisticated technology and art. Do any arms to the nature. At the same time, contribute new petals to the serenity of nature. Fabricated house should last over 100 years. And in this respect, by no means worse off than conventionally built house. We offer completion in 100 days, 25 years of construction warranty, 30% cost reduction, 20% materials are reusable, painting with putty work, UPVC windows, branded wires and other accessories. You can dream, we can make it possible. Take Heart Homes.
Cos- Cosmology brings us face to face with the deepest mysteries, questions that were once treated only in religion and myth. Good evening and a hearty welcome to one and all present here. It's a pleasure to have you all here on the fourth day of NOVA 3.0 for an interactive session on space exploration. NOVA is a collaborative venture featuring space enthusiasts and communities from leading colleges of the state, which includes GEC Thrissur, CET Trivandrum, Marathaneshwars College Kodamangalam, GEC Kannur, NSS Palakkad, GEC Idukki, RIT Kottayam, TKM, and Amrita School of Engineering. The initiative focuses on promoting space research and exploration as a bright career option and promises to offer unparalleled opportunity to learn from industry experts, network with peers, and explore the latest developments in space technology. This year's NOVA is sponsored by Tech Art Homes and Club FM. Now I invite the speaker and guest of today's session, Shri Ajay A. Potdar, scientist at Vikram Sarabhai Space Center, Trivandrum. He is a graduate in Bachelor of Technology, Engineering Physics from Indian Institute of Space and Technology, Trivandrum. Now I hand over the session to Shri Ajay. Sir, please.
Yeah, am I audible?
Yes, sir.
Okay. So yeah, I guess this is a discussion session and I have prepared some preliminary slides, I would say, just to pique your curiosity about something about astronomy. So like about me, I'll tell you something about me. I did my engineering physics in IST for 3 years, and after that I did a Master of Science in Astronomy Astrophysics in the same institute. And currently I'm working on ionosphere. It's a little bit different topic, but yeah, it has its curiosities and inquisitiveness. So anyway, okay, maybe I'll share a screen. Let's share. Can you see the screen? Can someone reply if they can? Okay. So let's just let's start with the Earth. We have seasons on Earth. So why do we have seasons on Earth? You know that in we have 12 months. 12 months meaning we have from January to December. Now when you so in the March, from January, let's go to March. In March, we'll have the Earth's axis, which is inclined at 23.5, 23.45, yeah, roughly, at an angle to the plane. This circle you can see, this is the plane of the rotation, and we call it the ecliptic plane. So the axis is inclined at 23.5. So when in March, the Earth's axis is perpendicular to the perpendicular of this plane in that direction. So meaning that both the hemispheres, when it rotates, it receives equal light. So that way, you can expect the equal amount of energy to be deposited in both the hemispheres. But as we go to June, we'll have the tilt towards this, meaning that suppose if we form a line here, so we'll have less amount of energy. Like if we just a minute. Can you see this? Okay. So if this is the axis of this side will be illuminated by the sun, and this side, this is the and if we draw this is the equator. This is the northern hemisphere. This part of the northern hemisphere will receive more light of the sun. You can see, meaning that more amount of sunlight is deposited over the amount of time. So meaning that 24 out of 24 hours of a day will have more than 12 hours of sunlight in this region. So meaning that's why it's a summer. We call it summer, and that's a summer in the northern hemisphere. So if in the in the September equinox, if we do the same thing, but this axis is actually in the same plane as this, so we'll have an equal deposition of energy. So it's an equinox. The temperatures will be fairly adjustable and fairly livable. So you'll not realize the difference, but you will notice a transition as we go to the December solstice. Here, what we see, if we draw this same plane, and if we have the equator, you can see that the this part, the northern hemisphere, which is receiving light, is less. So the amount of hours, amount of hours which will receive light in the northern hemisphere will be less than 12 hours. So basically, what we'll observe is cold because heat is lost. So that was just one. I just started with seasons. Let's look at constellations. You might notice that you might have seen that if you see in the night sky, you will see more than 12 constellations. But there we still talk about 12 zodiac constellations, mostly related to astrology and that particular subject. But why do we take 12 zodiac constellations? Why are there not so many other constellations? It's because if we look at the ecliptic plane and if we look at the position of the Earth and we look at the sun, so suppose in January, you from anywhere on the Earth, you look at the sun, you'll see Sagittarius in the behind. Of course, you'll not see this during the day. What you will look at is Gemini. This you'll record. You come here, and at that point you will see Sagittarius. January, this will go January, February, March, June. Around June this time, it will be Sagittarius. This is how you know that these constellations are there. Now, this is not of really much important in astronomy as such, but in the past times, in the historic times, these constellations were used as a time indicator of a particular year, position of the sun, of how the seasons will evolve. They could predict using these constellations, position of these constellations, if summer will come or if winter is receding, and these so many other things. Now that was zodiac. Let's go at. Okay, this is a pretty random topic. This is a Lagrangian point. So if you take a two-body interaction, you can always in two-body interaction you can always do like we have in gravitational. If you solve those equations for in 2 dimensions for gravitational positions as well as where a particular body should lie such that it is in a stable equilibrium as well as unstable equilibrium, because you know about those points when you were perhaps studying for IT and all, you would have noticed this is potential, this would be distance x. So you would have noticed they would have taught you about these points. This would be an unstable equilibrium, and this would be a stable equilibrium, meaning that if a body tries to go this way in the position x, but due to the potential increase in potential, it will try to come back here. So like an oscillating thing. And similarly, here, if a body tries to move this way, it will basically move away because it's potentially decreasing, and that's what a body will tend to do. And similarly, if it moves this way, it will escape that. So if you do this this analysis in case of the sun, the earth, and if you take another body of mass m, which is very small, you have to do some approximations for it to do that equations, including Kepler's laws. And what you get is that you get these 5 points: L1, L2, L3, L4, and L5, where the bodies are relatively in equilibrium. I am calling it relatively because at L1 you will be in unstable equilibrium in the axis of Earth and Sun, but you will be in stable equilibrium in the perpendicular axis. Similarly, for L2, we will have the opposite case, a similar case, and L3 and L4 and L5 are relatively unstable equilibrium. So why is it that we are discussing this? Why are these points important at all? If you might have heard, there is an Aditya L1 mission coming up, which is a mission to observe the sun. You know about the recent deorbiting of satellites, of SpaceX satellites. Roughly 30 satellites were deorbited due to some drag which increased in the upper atmosphere, induced by the by geomagnetic storm. So if this happens to our crucial satellites, it would be devastating for our systems. Since we are reliant on technology, we need to predict how this happens and at what time it can happen, how can we mitigate it. So what we are doing, what India has done is it's sending a Aditya L1 mission to this L1 point, meaning that at L1 there is little nothing. I would say there is no body there. So at L1 point, the satellite will be rotating in the sense orbiting about nothing. So that point, that way, if there is any sort of solar storm which is coming this way towards Earth, we will be able to like get the information about it before it reaches Earth, because solar storms travel relatively slower than the speed of light. So once we get the information here, the data is transmitted at the speed of light back to Earth. We can process it. We can predict if the solar storm can be significant. So these are the studies going on. Now there are other importances of these Lagrangian points also. Let's look at Jupiter's Trojans. So we have like the inner planets and we have Jupiter. These green points are these green points are called Jupiter Trojans because these are the L4 and L5 points about which Jupiter carries its carries asteroids which have been caught in that particular potential wells. So that helps the inner solar system. This decreases the amount of bombardment actually in the inner solar system. This is another implication of Jupiter. Jupiter is a really interesting planet, and yeah, we can discuss more about Jupiter later. Now let's go beyond Jupiter. Let's look at the nearest stars. We have Sun, and about 4.5 light years we'll have Proxima Centauri, Proxima and Alpha Centauri, which are the closest star system to us. And what would be light years? Like if we ever want to go from the Sun all the way to Proxima Centauri, it would take us 4.5 light years if we travel at the speed of light. This is and the first thing is we can't travel at the speed of light. It's very difficult as of now. And 4.5 years is a relatively small time, but then you have habitation issues, you'll have health, and basically Earth has got everything we need. That's a different topic for discussion. I just thought I would put that here. Now let's go beyond that. Let's look at our galaxy. We know that this is the shape of our galaxy. That this here inside is a galactic bulge. It's a galactic bar. It's a bar, and at the middle we'll have a black hole, supermassive black hole. I think it's named the Sagittarius A, and we have Sun in this particular spur. It's called the Orion spur, and this is our position in this whole galaxy. So this shape of a galaxy is spiral, and this is relatively what is commonly observed in many other galaxies. There are some galaxies in which you'll find elliptical shapes, meaning diffuse shapes, which is right at center. And as you go outwards, it will be diffusingly, the light will diffuse and it will appear darker. So, okay. Let's look at dark matter. I'll introduce dark matter to you here because dark matter is the particular subject which comes in discussion a lot frequently. So what happens is when we see a galaxy, what we look at is we can divide it into two parts. This is the this part, which we assume is actually a rigid body, a solid rigid body, and after that it will be like planets, like the solar system. So the farther the planet, this slower it will rotate. the less the angular velocity. But if it is a if we assume it to be a rigid body in this part, what we see is that the angular velocity should increase as we go outside. So when you put these together, you see that solid body rotation, the angular velocity should increase from 0 and so on. But at a particular point, you'll have a Keplerian rotation, because as planets, the outer planets rotate slower. Similarly, you should have a Keplerian rotation. But what we observe when we look at galaxies, even our own galaxy as well as other galaxies, we see that the galactic rotation increases, but instead of decreasing due to Keplerian rotation, it stays a constant. And like how? Like that is a really big question. That would only happen if the mass of the outer galaxies, because if something is rotating, and it is like if something is rotating, we usually see that the density outside is less as compared to the density towards the center. That should be the intuitive thing, right? But what we see is that if it were decreasing density outside as we go outside, it should happen in Keplerian rotation. But after some point, the galactic rotation curve, the angular velocity is constant with respect to distance. So why is that? Why does that happen? This can only happen if there is mass here, which we are not seeing, which we are not accounting for, because the amount of light we are saying, we assume it to be directly proportional to the mass. But there's something dark here which has mass and which we are not seeing. So that is the first concept. This is an actual light curve which we see from one of the galaxies. So you can see measure the velocity from starlight, as well as hydrogen spectroscopy. From that, you can see that the angular velocity is increasing or roughly constant. The trend is similar across all spiral galaxies. So that means that there is some dark matter here. So that, I guess, that would be a first introduction to dark matter. As to what it is, that is a question we can discuss about it. Now let's look at the expanding universe. So when you look at expanding universe, we will always observe the case. There are two galaxies, and it is expanding with from a center point. And if a galaxy sends a EM wave towards our galaxy, the wavelength increases. Of course, that is true. The wavelength increases, meaning that the wave is redshifted. So redshifted meaning the wavelength is increasing. If a galaxy would be blue shifted, that means the wavelength is decreasing. That means the galaxy is approaching towards our galaxy. But this is a general picture. This is just to visualize. In particular, there is no particular point of origin. And you can actually imagine, it's difficult, but you can actually try to imagine that every point is the center point of that particular our universe, and everywhere it's expanded. So that is one thing. Now let's look at the cosmic microwave. You might have seen this many times. So what it means that these are the fluctuations we see from the average temperature. Difference from the average temperature. The average temperature is 2.78 Kelvin. Okay, when you look at the different regions in the night sky, the fluctuations are of the order of 500 microkelvin, which is very small. So if you take an average of all of this, and if you put together a spectra, this is just a temperature map. Okay, if you put together a spectra, you will see this as the curve. Now you might remember about black body radiation. At like if a black body basically absorbs everything, all of the radiation falling on it, and it emits at a certain temperature. That temperature will be specified by this particular peak. So when this COBE is an instrument, it actually did these observations at all the wavelengths, and it put together this spectra. So what you can see is that the spectra fits the actual black body, thermal black body at 2.78 Kelvin, meaning that this are cosmic microwave. The universe, the edges of the universe, is basically a black body, and actually, it's the most perfect black body ever recorded till now. So, yeah, that was pretty much it. I wanted to give you all an overview regarding how intense and how interesting astronomy can be. So, if you have any questions, please send them my way.
So there is a question in our
Yeah.
chat post that says, "Can you please tell us about CubeSat?"
Oh, I actually, yeah. The thing is, I'm not really working in that field, but CubeSat, apart from the dimensions and like which particular CubeSat, I guess there are many CubeSats, and because this is mostly, yeah, I don't think I'm the right person to ask that question, but I can refer someone to you maybe. Okay, there are some interesting questions coming up. How satellites are able to revolve in Lagrangian orbits without the presence of a mass at the center? That is a good question. You don't need a mass at the center. That's the interesting thing. Why do you not need a mass at the center? Because all you need uh, here, if you erase all of this, uh, all you need at a point is a potential. All you need as a point is a potential, and the body which is revolving should have a particular velocity when it enters that potential well. So when you enter a potential well, you need to have a velocity that should be just enough to stay in that particular orbit. So a planet is a planet or a star or basically anything. A large body is basically a potential well. You can try to imagine it in the potential dimension. It's like it's not really intuitive, but you can try to imagine that this is the sun, and these circles which are encircling these concentric circles are getting closer uh, as we come towards the sun. That means the potential is negative, and it's increasing. In negative sense, it's increasing as we come towards the sun. So if a body is put in enough with enough velocity, it's basically moving in this potential well. That's how we should uh, imagine that. Okay, I hope I have answered your questions. How satellites are able to revolve in Lagrangian orbits. Now, could you explain about China's artificial moon? I don't think I've heard about that. Uh, I don't have any information about that, so I'll refrain from answering that. Why does the mass of a body increase as it approaches the speed of light? Okay, we will be going into special relativity here. Uh, okay, maybe one reason why you can assume it is that uh, see when you have a mass body with a certain mass. So okay, it's the factors. All of the intuition about this comes from mathematics, and I know it's counterintuitive. You can't. There is no proper explanation for this, but there is a particular equation that the mass is mass of a. Like, I think you would know that mass of a body is equal to a mass into 1 minus b square by c square. Is this correct, or is this in the denominator? No, sorry, it's in the denominator. Yeah, sorry, divided. So this is the equation, and as for why it happens that way, you can try to look into special relativity for that. It's I don't have an intuition for that. I'm sorry. Can ordinary particles decay into dark matter? Okay, these are pretty advanced questions. Yeah, I don't think ordinary part. Yeah, I really don't know if ordinary particles can decay into dark matter because you don't know what dark matter is. If if you can tell me what dark matter is, maybe I can discuss with you why if they would decay into ordinary, why they would decay into dark matter. And can you please tell us about how to become an astronomer? Stop it. Okay. Yeah. So yeah, I actually there are to become a scientist in ISRO, there are various recruitment. ICRB conducts recruitment throughout the year, and there is a LinkedIn post. Maybe I can share that with you. Uh, One of my seniors, he talks about how to get into ISRO. You need to have a knowledge, fundamental grasp of for physics. You need your physics to be good. If you want to be an aeronautical engineer, you need mechanical to be good, and of course, electronics is also there. There's some other streams also, but if you want to be a scientist, scientists need to have an expertise in uh, either aeronautics, avionics, or electronics, or physical sciences. Even physical sciences are also fine. So, and there are ICRB recruitments also. You can go through that also. And if you are in 11th or 12th, perhaps maybe you can also attempt JE, and you can maybe apply for admission in IST. IST has I am from IST, so IST has a clause that it can give you a placement in ISRO. Okay.
Sir,
Yeah.
so when you take the picture of a galaxy, why is there an extremely bright thing in the middle?
Okay. That is a good question. Yeah.
Like there is supposed to be a black hole there. So how is there an extremely white thing?
Okay. So I'll tell you. The reason is there will be a black hole there, but the black holes. You know what is event horizon?
What?
You know what is event horizon?
Yes.
Yes, event horizon is the distance from the center of black hole wherein the light cannot escape.
Yes, I know that.
Okay. So
Yes.
from the event horizon distance from the center of the black hole is not as large as compared to how much dust is around that particular black hole. Like for example, you look at our own galaxy. Uh, if the event horizon size will be very small as compared to black hole. This is actually an exaggerated size I've drawn. But the event horizon small will be very small, and basically all the matter that is revolving around that particular black hole is uh, it's very dense, and when density increases in space, you will have collisions, and when you have collisions, there is a chance that basically when you're colliding with something, you are exchanging energy, and the momentum, the kinetic energy is converted into another heat, so heat potential. There are many other forms of energy, but majority it becomes light, and the heat, light and the heat become. That's why it's very bright in the center. So that's why the farther you go away, it decreases. Yeah. I hope
Sir, but our galaxy has existed for a long time.
okay.
And so will that why is the time not enough to uh, take all the stars out?
Oh, yeah. Galaxies have existed for a long time, but till now the time hasn't been enough to like extinguish the stars. The stars are in a process of, you know what happens? Stars form,
Yes.
they die, and
Yes.
from the ashes of those dead stars, smaller mass stars form.
Mm.
And this process keeps on going. And I think it will be like, I don't know, I can't say a number, but it will be a long time before all the stars extinguish.
Okay, sir. Thanks, sir. Thanks, sir.
Okay. Okay, let's take this question. Okay. does the satellite revolve in a plane which is perpendicular to the displacement between Sun and Earth in case of L1 orbit? Okay, like 848 5s. I'll maybe show you a diagram of how it actually revolves. So if this is the Sun, and this is Earth, and this is the L1 point, what happens is the satellite, if you connect this line Earth, this is Earth, and this is Sun. This is the L1 point. The satellite will revolve in this direction. It will be in a plane which is perpendicular connecting these two lines. Yes, so you are correct. Yeah. Now Arnav asks, how do we generally measure the distance between Earth and Star? Okay, that's another good question. There are ways actually. So there are many ways. I'll tell you about two of them. Okay, so if we are here, this is Earth and this is star, very small. And what happens is at a certain point of time, you will see a star to be here. After some time, the star might move a little, just a little. This theta. If you find, this is called parallax. Because when you basically, if you put a finger in front of your eyes, from both of your eyes, you'll see different positions of the finger. But for a star like that, you can, using the angle theta and our position here, you can actually find out this distance, because you know this angle theta and you know how much Earth will have moved in that time. You can find out this distance, and you know what is theta is equal to. I think what is this? Okay, there is another method, but maybe this is involved in that. Suppose this is S, it will move, so S by this D.
Excuse me,
okay,
sir.
Yeah.
Sir, are you drawing something because the slide got stuck?
Oh yeah. It did not. Okay, maybe I'll draw it again. I'll explain a better thing. Can you see it now clearly? Hello?
Sir, currently the slide which is written like our galaxy and dark matter is visible.
Okay. Just a minute, I'll okay, now can you see this?
Yes, it is visible.
Okay. So yeah. Okay, how do you determine the distance to a star? That is a good question. So if you know that if you look at a star, you are basically and if you look at the radiation which is coming from the star, you plot that against spectra, like the frequency and the power. Like the spectra, if you plot, you know the black body spectra. What we do is we assume a star is basically roughly a black body. So when you look at the black body, a star, you do this. You plot the spectra. When you are using, there are many spectra. 2 mass is one of them. I've done a lot of work using 2 mass. Anyways, if this is sun, you plot a power spectra, which is the power with respect to frequencies from all visual, let's say visible frequencies. So starting, I guess, roughly 450 nanometers to, I guess, 700 to 750 nanometers. I might be wrong, but yeah. So if you get a spectra like this, what you can see is there will always be a peak. And from that peak, you can associate a temperature. Okay. And actually from this, you can calculate a brightness of the star. there is a standard in astronomy. From a temperature you can calculate the brightness of star, and brightness of star also by integrating below this curve. And when you calculate the brightness of a star, you basically know with the, you know the basic inherent property of the star. Now this is for sun, but if it were for another star which is far away from us, and if you are doing that, you will get a similar curve, but it will be dimmed. Meaning, if you get something like this, and you get a brightness from this B2, let's say, if the brightness of this is B2 of the star, and the peak corresponds to a different temperature, say T2, you can actually determine the distance by saying that by assigning a certain extinction coefficient from year to year. We can say brightness is we usually express in terms of luminosity. So from a distance from the star to Earth, we assume that there is some extinction, and from that extinction we calculate how because a point source, as it radiates outwards, the luminosity decreases with distance squared. You know that, right? So once you do that, you calculate the brightness, you know the temperature, and when you do this, you fit that. I hope I'm clear about this. Maybe I'll tell it to you again. So you have a brightness. Okay. When you find the when you get the spectra of this particular star, you get the spectra, you will know the temperature. And when you know the temperature, you know the inherent brightness of the star. You actually can deduce it using mathematics and physics. So from that brightness, this is a theoretical, and there is a brightness which actually will be observed. This brightness will be observed, and when you compare this theoretical brightness and the theoretical brightness and the observed brightness, you can actually determine how far the star away from us is. I hope that clears your question. Okay, how do we check? Okay, but I think similar behavior is in and like electronic. I am like, let's not talk about. I don't know actually. Okay, maybe I'll go on to the next question. Could you explain synchrotron radiation and its physics? Yeah. Okay, synchrotron radiation is when like when an electron rotates about a magnetic alternating electric field. There's an alternating electric field that is for a okay. Yeah, synchrotron radiation. We have a movement in electron. Electrons are basically rotating, gyrating at relativistic speeds. This is due to the energy they are provided from a nearby supernova or basically a star. So they get enough energy to rotate at relativistic speeds, and we have radio emissions. Now, what do they mean in astrophysics? Okay. As far as like what my research is concerned, I had observed a particular galactic dust bubble. A dust bubble is basically something in the galaxy. It's a nebula where you have a large presence of hydrogen. The hydrogen is ionized because we have ultraviolet radiation from a nearby star. The star can be a giant star or anything, but we have ionizing radiation from that star. And once the star ionizes the hydrogen, we'll have hydrogen ions and electrons. So when these electrons, when they get enough energy due to more, there are different mechanisms. They actually radiate in not just synchrotron. There is thermal radiation. They have the thermal radiation characteristics are different. There is synchrotron radiations and its characteristics are different. So, yeah, what does it mean when a particular radiation? If we see synchrotron radiation in a particular galaxy, particular dust bubble, or anywhere in wherever we are observing, it means that uh, that means electrons are accelerated to relativistic speeds, meaning that there could be a really uh, energetic source, like there could have been a supernova recently, that is possible, or something. Yeah. Okay. Maybe, yeah. I think that should answer your question. Which is better, aerospace engineer, BTech, to work as a scientist? I think you can do a BTech in aerospace engineering. Yeah. You can get aerospace engineering, like in ISC, there is a BTech in aerospace engineering for 4 years. And if you get good grades, about 7.5 CGPA by the end of that, you can get they might give you an option to be placed in ISRO. Yeah. Okay. Sir, UV stars, millions of years, it will be stop glowing. Become black hole. So what about? Oh yeah, the sun will actually become a nebula and a I don't. Okay. Yeah, it will become a nebula and so black. Yeah, it will become brown dwarf. It will not become black dwarf, because black dwarfs need the star to have a lower mass. Brown dwarfs have some energy. It will still radiate, but not at, of course, the fusing hydrogen fusing temperatures. So yeah, that's pretty much it about the sun. There is more time left for a sun, like 6 billion years. After a sun will approach its red giant phase. Also, a sun won't be able. Yes, white dwarf or brown dwarf. Yeah, you can say that. There are many papers regarding that. You can read those. Yeah. Is there any possible way in which we can see distant stars much earlier than the time they used to travel to reach to us? Sorry, I read that question again. Is there any possible way in which we can see distant stars much earlier than time? So, maybe Prachi Verma, can you maybe reiterate that question and we'll try to answer that again? Seems like a good question. How to get an internship in VSSC as a BTech student? If you are, I don't think there are any openings for at least physical sciences for internships. But if you really want, if you are keen about an internship, maybe you can just for the sake of any project, maybe you can mail a particular guide. You can look at their work, see if it aligns with your research, and mail them about it. Pique their interest, make sure it does that, and once it happens, they might call you to VSSC for an internship. And because I don't think VSSC gives out any interns for advertisements. Yeah. We know that stars we are the ones that looked like what years ago. Do scientists have any idea how much stars have gone supernova now? And if yes, how do they do? Oh yeah, this is like an interesting question. We definitely have no idea if the stars that we are looking at right now are exactly as they are at wherever the stars are, because of course the light year difference is there. So how do we know if a star has gone supernova? Majority of the stars in nearby our solar system are I'll show you that. Yeah, from 4 light years onwards and 6 light years onwards, it starts. So even if we knew that if a star is going to go supernova, it will be only 4 light years, 4 years minimum before we know that. And even if we were to know that, there is actually a certain fluctuations. Like in the case of Betelgeuse, you might have heard about that. Betelgeuse is currently going increase dimming and brightening in its magnitude, magnitude as in luminosity. So that is an indicator that a star is running out of fuel. And when a star is running out of fuel, at that size of the star, it can go supernova. So yeah, that is how we would know. Yeah. Any other question?
So then I will give you a question that we collected from the registration form.
Okay.
Why the cosmic microwave background is almost equal whenever, whichever direction you measure. You got
Yeah, it's not okay. The cosmic
microwave
I
background is almost equal.
I
Whichever
hope you can
direction you measure.
I hope you can see the screen. Yeah. Yeah. It's not actually equal. It is almost equal. Yes. Because when we are looking at the cosmic microwave background, we are looking at the edges of the universe, basically. You are eliminating all the stars. You are looking at a cavity in which we are there. So there is actually a lot of research going on about this. And why is it like that? You're looking at the cavity and you're looking at all the material aggregated inside that cavity. So there is, I mean, this is a really astounding observation. But as to why exactly it is happening like that, I don't have an answer. So yeah. Maybe next question.
How can solar flare shut down the power grid?
Okay. So solar flares, when solar flares happen, what happens is that a solar flare can eject a lot of high energy particles. High energy particles are basically protons or neutrons. Electrons actually get electrons recombine because at that energy and when they cascade down into the atmosphere, electrons combine with neutral, even with neutral as well as they have some reactions. But if a proton is there, which is heavier, and if it has like let's say if a proton is there and it has a very high velocity, what it does is it can go through our electronic systems. And since all of our current electronic systems are based on semiconductor devices, the ions, the high energy particles can go through inside them, and they can disrupt the flow as well as storage capacity. What we do when we use semiconductor devices, we usually are monitoring the position of electrons where they are present in the semiconductor devices. So if the ions pass through them, they will alter that. It's not just one particle. It will not be just one particle. There will be many high energy particles which will basically spread out throughout Earth, and that way they can disrupt the whole grid. It's not just the semiconductors. There are you can even have cascading effects in the higher atmosphere. So that is another thing. But yeah, I hope that's it. Because I'll tell you one fact here. If like when astronauts sleep in space, when they try to sleep, they sometimes observe white streaks of light. It's not necessarily white streaks of light while their eyes are closed. Why do you think that happens? It's because of these high energy particles which exist in space, and they actually give energy to the material inside our eyes, and our receptors inside our eyes, they detect that. Okay, maybe next question.
So we have questions in our chat box. I think we can. Go through
Yeah.
that.
Do you have any concept or idea on how we can achieve space travel, distance galaxies in short time? The thing is, in general relativity, you have concepts of bending of space. They have many videos about trying to bend space in such a way that you are entering a space in another coordinates from one coordinate system, like a discontinuous thing. But that is all of it is theory. So, and of course, you might have seen about hyperspace travel and all. So, as far as it is concerned, special theory of relativity is still at its, I mean, uh, it's still young. Maybe in the future, if we find something which we can, if we are able to generate that amount of energy in order to curve space to our liking, maybe we can do that. In what ways are exoplanets checked for life availability? Okay, that is a good question. So, uh, exoplanets are a really interesting topic. I'll just So let's say we are observing from here, like let's say this is a star we are seeing as it is, and there is a planet which is moving about the star. It's rotating about the star. It will not be, of course, at this scale. This is large, but at this particular point, let's just assume it's like this. What happens is, if the planet's orbit happens to cross this way of the star, in our frame of reference, what we see is that this particular this particular planet is transiting this star. So when a planet transits this star, if it comes at this particular point, we'll look at the brightness curve. Okay, look at the brightness curve of this star. Uh, till here, the brightness will be constant, but once it starts coming towards inside, the brightness will decrease, of course, because you'll have a smaller area of light from this whole disk you're observing. And it will, at certain point, at this point, you'll see it will become constant till up to here. And it will start increasing after that. Now, this is just brightness. This is just brightness. And when you say brightness, you look at the aggregate of all the frequencies. So that is what you do for brightness. But when you can go into spectroscopy, so these planets have atmospheres, a very small atmosphere, but they will have. And when the light passes through this atmosphere, you can do spectroscopy. And if you get a peaks, in this case, you'll see valleys because this is a colder atmosphere. The atmosphere will have temperature less than the star. So that means if the actual spectra of the sun is, suppose say this, then if a planet comes here, if you see dips, small dips here, here, you will see basically you can find out which of these species cause these chemical species. This might be hydrogen, or this might be helium. There's lithium. There are actually some chemical species of the spectra of which we don't know. We are still in research under that. But if you find out these chemical species, you can give a prediction that this planet might harbor life, because for harboring life, what we need is water, H2O. The planet should also be at a distance. We'll also try to measure the planet's temperature. There are other methods to do that. We'll look at water. We look at carbon, the atmosphere. We look at, I think sulfur is also there, nitrogen. Basically, all the essential elements for creating life. All of the elements are essential, but the first half of the periodic table is more important for sustaining life. Okay. Also, the CERN experiment, which recreates the condition of the early universe. Can we map how universe is expanding through the universe? Experiment also. Sorry, I'm not able to understand this question. I'll repeat again. Oh, I don't think I don't think CERN is trying to recreate the conditions of the exact early universe. I mean, we are accelerating particles for sure to discover more about particles themselves, and not, we can't say for sure that CERN is trying to recreate the conditions of the early universe. Yeah, because once we know about particles themselves, we might be able to understand what happened in the early universe and what was there. Well, we call it a cosmic soup. So I don't think you can actually get the cosmic soup. The cosmic soup is basically the aggregate of all the particles and everything that was there before the Big Bang, before and during the Big Bang. Can dark matter be artificially created? I have really no idea, because it's something which you don't know about. I'll tell you one thing, because we as humans, we experience, feel, and touch. All of these things are related to actual matter things which we can touch and feel. But when it comes to experiments, uh, when it actually comes to these experiments, it's difficult. The fact that dark matter, there are some papers, but I really don't know how would you actually define a dark matter, because normal matter you can define as something with a proton, neutron in the nucleus, and electrons revolving around it. But how can we define dark matter? That's it. Question itself is a big one. There might be actually progress in the particle physics field. So I don't really know answer to this. Can dark matter be created artificially? Yes. Any more questions? Okay. Why is time different around different stars? Can you talk about this? Time is different around different stars because, okay, first thing, time is even relative on Earth. Like it may be 12 o'clock here, but will be 12 o'clock minus 5.5 hours in Greenwich, UK. So what we do is time is relative. Sorry. Yeah, time is basically relative. Now we will take the time for ourselves, which is most convenient for us on that particular planet. Yeah, and twins paradox is basically, yeah, if there are twins, if you send one of the twins on a spaceship which is traveling close to the speed of light, maybe around maybe a distant star or a planet, if it goes, by the time it comes back, the twin will have aged relatively less as compared to the twin on Earth, because the theory of general relativity predicts that the time is relative, and when you say relative, the frame you are matters. The faster you are going, the slower the time is for you. And how to actually explain this? Like I mean, there might be a better intuition behind this, but I won't be able to give you that. So, what actually is gravity? Is it a space-time curve created by any heavy mass or something else? How gravity affects time? And we know that black holes has a very strong gravitational force. How does that work? So, yeah, gravity is there are Newton's. According to Newton, it's just a force. According to Einstein, it's a space-time curve, which is basically created by heavy mass. Maybe we can create gravity in by something else. So that's gravity. You remember the Lagrangian points? Okay, in the Lagrangian points, there is no gravity there. It's the aggregate of gravity that is making you orbit around that point, L1 point. But there is no heavy mass there. So there is no bending, or there is no space-time curve there. Even if there is space-time curve, it would be interesting to know how it actually bends around a Lagrangian point. So maybe if someone of you is involved in maybe modeling or something, you can try to do that. Try to do a 3D modeling of that. It can come out as interesting. How actually the space-time curve evolves around the Lagrangian points. So is it the thing is, actually anything in this world, as a scientist, we all have different theories. and what is accepted best is one thing we rely on. Since Newton's was the first theory and it was generally acceptable, in a way it was generalized, it was accepted. And Einstein came with this theory of space-time curve. That is interesting. The intuition behind it is very difficult, but it's not impossible. You can try to do that. You can try to read that, because the mathematics involved in that is not intuitive at all. So when you say a space-time curve, it is something that is trying to pull us in. So, and when something is pulling us in, the time slows down. So basically, you might have seen about those videos about a black hole, and there's a black hole and there is a well which is endless. There's a star which has a well, a proper well. So basically, the more curve the space, more mass an object has, the more it will bend the space time. So yeah, of course, black holes will have a strong gravitational force. Of course, they have a strong gravitational force because they're basically pulling it off everything that is there, and their mass is so strong. Their mass is enough to pull even the light at a certain event horizon inside. So if you try to imagine a classical sense, if the mass, as I explained to you, event horizon is the distance from the star at which distance from black hole center from which at which even light cannot escape. So meaning that if you are putting in more mass and if you are increasing the mass of the particular black hole, the black hole can shrink because you're putting in more mass, and the matter will want to come together because of the gravity. And as to how it is bending space-time curve, it will be interesting to actually do that calculation. I myself want to do that. I'll do that sometime. But once you do that, the event horizon distance from the center is increasing. You'll see that the size of the actual black hole can be decreasing, but the event horizon will be increasing. That's just one thing I think it will be interesting to think about. Doing the actual analysis of this could be interesting. Yeah. Any more questions? Parallel universe. Yeah, I am influenced kind of by these this MCU and DC stuff, but parallel universe, there is observationally, I don't think it's really observationally. It's difficult to find evidence. How would you even find an evidence of parallel universe? Is your intuition evidence of parallel universe? Like, if something happens, if you get a deja vu, maybe someone else in some other universe is experiencing something you thought you experienced once upon a time. I mean, these concepts are interesting, and they definitely do need a lot of work. And I would say that the more like beyond the realm of our imagination we go, the more mathematics and the more generalized we need to get. And when we say generalized, because Einstein's theory of relativity, this general theory of relativity, is a general aspect. The mathematics he put forward is a more general aspect of the classical thing, and you can actually apply that thing to even quantum mechanics. You can apply the quantum mechanics mathematics and on classical objects, but then you'll have to do a lot of calculations. It's easier for us humans that we want the answers to be simple. So even Einstein's thing you can apply there. So for a parallel universe, you basically have to come up with something which actually explains that. So mathematics and physics are involved, and as scientists, I would suggest that these topics are interesting. They are interesting, and it's not. I would recommend that these topics can be pondered upon, but you should make sure that your footing is on strong fundamental physics, and you can grow from there. From there, you can branch out. You can do quantum, we can do general relativity. Putting this, even the unification of quantum and electromagnetic theory, it's a very big topic. It's a very difficult thing to understand, and I don't think it's anyone can understand the whole of it in their lifetime. It's for the whole of humanity. So yeah, that's basically my view about not just parallel, basically all of science. Yeah. Any other questions?
I think no one is left to give a question. Anyone have anything else, John? Okay, then let me invite Deepthi for the vote of thanks. Before that, I will be sharing a feedback form in the. Okay, one question.
Yeah. Please explain how the luminosity and temperature factors are affecting the way in which we are measuring the distance between Earth and Sun. Okay, so okay, maybe this. Okay, you have a star. You have a star which is very far away from you. You at on Earth, you find out the spectra of that star. This is observed spectra, okay. Observed spectra. And once you find out the observed spectra, you basically integrate along this thing. You want the total brightness that you're seeing along it. Basically, at all the frequencies, you integrate that and you find out a luminosity, also called as brightness. Maybe for our case, we'll do that. Oh, you want an exact formula for that? I think it's something of okay. It has been quite a while, but something if this is the L observed and L expected. If there is the same star, if you were at a there's standard that if the same star were at a distance, I think 1 AU, we would have seen it at a brightness of sorry, at a this L EMP. So that way, L observed upon LEMP, right, LEMP. Now, if this is suppose say radius r, this is 1 AU. So how do we do that? If there is a source here which is emitting at power say p, then the power which you receive at a distance r from the source is calculated as p by 1/4 pi r square, right? Because it expands in a spherical shell sense. So p upon 4 pi r square. So this if this is radius r, and you know that it will be, you can find it out at 1 AU. You know that it will be at L EMP, because see, I hope I made myself clear that once you see the spectra, observe spectra, you can find out the temperature, and from the temperature you can actually construct the theoretical black body spectrum. From that theoretical black body spectrum, we can find out this luminosity. This will give us the luminosity of expected or theoretical. Now, once you do that, p upon 4 pi r square is this thing. So you basically take the ratio. So L observed is proportional to power of the actual star upon 4 pi this r square. And for this case, it will be L expected is proportional to power upon 4 pi 1 AU squared. 1 AU squared. Now just divide this, take a ratio of this. L observed upon L expected is equal to 1 AU squared upon R squared. Yeah, I think you can get from this. and you have L observed, you are expected. You can find out R. There is a logarithmic relation for log L because we use luminosity in a logarithmic sense, and it is convenient for astrophysicists. So you can explore for that later. Yeah, maybe. You, yeah.
Anyone else? If you're typing something in the chat box, you may raise your hand. Okay. I hope it's good. Okay, then let me invite Deepthi for before that, I'll be sharing a feedback form in the chat box. So you may fill that form in order to get the certificate. Okay. Deepthi, you may continue.
Thank you, sir, for this informative session where we could learn more about astronomy, about Lagrangian points, dark matter, black holes, and much more. I would also like to thank the event coordinators and the participants for making this session a success. It was wonderful to have you all here. We welcome all to the conclusive day of NOVA 3.0, which is set to be held in person at Government Engineering College, Thrissur on April 1st. With this, we conclude the session. Thank you, one and all.
Thank you for having me.